Okay, hi everybody and welcome to my video for the InterSystem Tech Video Challenge. And today I'm going to be showcasing to you our solution for finding certain genes inside DNA sequences using the InterSystem IRIS database, vector database. The solution for this project or problem was actually developed a week ago at one of the hackathons that has been happening at Brno, Czech Republic, where we went to with my friends from my university. And in a team of 4 people, we actually came up with this idea that I'm going to be presenting today. And those people were Martin Benedict, Yannick Gibson, Ivan Dostal, and me, Filip Kašpar. First of all, I will briefly discuss what is the problem and what we had to do and what we had to solve. And then I will show you how we actually managed to solve it and how we use the InterSystem IRIS vector database. Okay, let's look at it. So I hope this picture is gonna clear things up a little bit. But before we're gonna actually look into how this all works, I wanna briefly talk about why we even care about this issue. And the explanation is fairly easy. Let's assume we have a few patients that we need to treat for some diseases. And those patients, we want to give them antibiotics. And we want to make sure that those antibiotics would work on them, that they are not resistant to them. How we can do that is exactly how this how this picture shows it. Um, we take the DNA sequence of our patient and we check if the gene representation of the antibiotic is in the DNA sequence of the patient. So if let's say this is the gene representation of some antibiotic, and we are checking if this string is in the DNA sequence of our patient. If that's the case, then we say the patient is resistant to these antibiotics, and we wouldn't give them the antibiotic since it wouldn't do anything for him, and it wouldn't do anything good. It wouldn't solve the issue, the disease that he is having or she is having. Um, so this is the idea behind why we want to check it, because you want to make sure that we can actually give the person those specific antibiotics. Uh, Also, there is worth mentioning one problem, that it's just not simply seeing if this string is in this if this substring is in this string. Um, because the machine that gives us the DNA sequence that reads the DNA of an organism or bacteria, it doesn't read it always correctly. So sometimes it can misread a certain character. So maybe there was an A in here, but he reads it like as a C, or maybe there might be like more characters in here that he didn't read, and many more flaws that the machine has. So it's not just like simply checking if the substring is included or is in the original string. There are a few algorithms that solves this, but we tried to look at a different way for this problem, and we came up with different solution that combines both an AI and also those let's say traditional algorithms that solves this problem. So how we did this was we took the DNA sequence from the machine and we fed it into our transformer model. The transformer model then outputted a vector representation of the DNA sequence. We then took this vector representation and we put it inside our IRIS database, and we just stored it in there. Then we did the same thing for our genes that we wanted to check. Those are you can take this as antibiotics. It's just represented as a gene. And then we took our genes, antibiotics, and we do the same thing. We fed them to our model transformer, and we get some vector representation of this gene. Uh, we then that is not stored in our database. It's stored in our program because the user can define a certain antibiotics. But of course, there might be a thing that let's say a user wanna store certain antibiotics in the database, that's also possible. So yeah, it's up to the user if he wants to just have it in their program and change it, because it's fairly quick to calculate the vector representation of a few genes, a few antibiotics. So yeah, it's up to the user if they wanna if they wanna have it in the program or store it in the database. But then the program gets the vector representation of the gene, and since the program has access to all the DNA sequences in the vector representation, then we can ask the database to give me the, let's say, 50 or 100 closest vector representations of the DNA sequences that is somewhat similar to my vector representation of my gene. So it's just basically finding uh, a similar DNA sequences to the gene we provided. So let's say I have some antibiotic, and I'm asking what are the closest DNA sequences that I have in my vector database. When we get back those 100 results from our database, those results are highly probable to have this gene in them. So we can then just use the, let's say, traditional algorithms to check if the gene is actually in them. And in case we find the gene in them, we just say that the organism is resistant to them, because the organism, the DNA sequences come from a single organism. So that's how we determine if certain organism or bacteria is resistant to a certain antibiotic. Okay, so I hope this explained it a little bit, and now I'm gonna show you how it's being done in the code. So let's look into that. In the code, we have it all written in Python, and so we have a main class, IRIS database handler, which sets up the database right here, and there is bunch of methods that can be called from the class. Uh, the main methods are to create a table that hold the information about the DNA sequence. So you have some barcode, which is just the organism or bacteria that the sample is taken from. File path, where is it stored in our disk, so we can reference to it. Index, that's the index of the DNA sequence, because we have a file that has multiple DNA sequences in it, so we want to index which DNA sequence it is from in the file. So that's the index, and then you have a sequence string that is just what we saw in over here. That's just the string over here, and then you have the sequence vector. That's the vector representation that is over here, and then oh yeah, and then we also limit the vector to what is the dimension of our vector that we get from our model, which is in our case 768. And then as the last thing, we say which model we used for calculating the vector representation, because we used multiple models, so we have also a field for that over here. So the two main methods that we have over here is insert embedded sequence, which just takes the vector representation of our string of the DNA sequence and puts it into the database as a vector. That's the you can see over here, to vector. That's the only thing that this method does. It just insert record into the database. You can see over here that we can insert multiple records at the same time. So we have let's say 1,000 sequences. We can just feed one data frame into this method, and we'll get all the sequences into the database. And the second method is our search method, and this one takes the organism, the search vector, that is the antibiotics that we want to search, and the model name. So you can specify on which data we should look into this antibiotic. So how it works, it's just basically it's using the vector cosine function that it's being implemented by that is being given to us by the IRIS database, and we just simply insert the antibiotics vector, and we look into the closest DNA sequences that might have this antibiotic vector in them. We execute the SQL query over here. Over here, we execute it, and we get the, let's say, 100 results back. We define that result number, so we can change it by in here. So we just get, let's say, 100 closest results to our antibiotics, and we return it to the program. I think that's all from our IRIS database handler, and we can take a look how it's being actually done in the solver. In the solver, we have this one function that is called solve, and that uses the IRIS database as well. And how it works is basically we get all the genes that we wanna, the antibiotics or the genes that represents those antibiotics, and we wanna convert them into their vector representation. So that's what we are doing over here. That's the get embedding function. When we get all the vector representations of our antibiotics, we move it over here where we iterate through all the antibiotics or genes we wanna find in our database, and in here we query the database with the organism we wanna check, the model that we are using, and we wanna look, and the gene. So that's the vector representation of the gene in string data type. So we call the function that I explained here. We get the results back, the 100 closest results, and then we use traditional algorithms such as Waterman for finding if the gene is actually in the DNA sequence. And we repeat this over and over and over, and at the end we get this is the polling thing for some statistics. But at the end, we get results for every gene that we check in the DNA sequence, and if it's been true or false. This is just some mock values, but this is how the outcome actually looks like. So if you look into the database in our in the web browser, we can see that we have a DNA scheme sequences over here. And if I open a table, which I open already over here, it's quite big, so I open it beforehand. We have the barcode, which is the organism, the file path, the index in the file, the sequence string, and sequence vector representation, and the model we use for it. And this is how the database look in the web browser. So yeah, so this has been a showcase of our project that we worked on during Hackathon, and I hope it's been understandable. And you can also check our GitHub repo where we have more information about our project. There is also a report in PDF that you can look into. Okay. Thank you so much for watching this video, and bye bye.